So today we're actually going to be doing a geometry fact together. And actually this fact only involves 4 points. And so we start with an equilateral triangle ABC. Right, and we're going to draw the circle that goes through points A, B, and C. Right, and then we're going to pick P to be any arbitrary point, right, on minor arc AB. So P could be anywhere along this arc here. And so just using these 4 points, right, and P is actually a variable point here, what do you think will be the claim that we will make about A, B, C, and P? Just only involves these 4 points. Well, now that you've thought about that a little bit, I'll tell you what the claim that we're going to be trying to prove today is we're going to be trying to prove that AP, the length of AP plus the length of segment BP, is equal to the length of segment PC. And so with this in mind, try to prove it if you like, and then when you're finished pausing the video or so, we'll actually go through a few different solutions to this problem in this video. So yeah, pause the video, and when you're done, we'll be continuing onwards with the solutions. So the first solution we'll be discussing in this video to this question is it's actually going to be more of a constructive proof. And so a lot of times when we're doing stuff like length chasing with these equilateral triangle problems, it's a good idea to construct actually equilateral triangles. Why? Because we already have a lot of 60-degree angles in our configuration, and equilateral triangles give us a nice way to prove. It gives us a nice way to compare equal lengths to one another. So if we're having problems involving lengths in equilateral triangles, you get a lot of 60-degree angles. It's good to try to construct some equilateral triangles in the diagram. And the other thing that we have here too is that when comparing lengths, it's nice to try to make the problem one-dimensional. And what do I mean by that? Well, we have these segments here of our AP and our BP. These things are all on different lines, right? And so it would be really nice to try to make them all like try to one-dimensionalize the problem in the sense that you're trying to prove, or you'll see what I mean. So first, with these ideas in mind, first you know that since ABC is an equilateral triangle, you get that all these angles are 60 degrees, right? And then, so if you look at arc AC, right? By the Star Trek lemma or the inscribed arc lemma or whatever it's called, you get that APC is equal to angle ABC because they point to the same arc on this circle, right? And so it will follow that angle APC is equal to 60 degrees. And so, and actually by similar logic, right, if you look at angle CAB and angle CPB, you'll get that angle CPB is also equal to 60 degrees, but I'm not sure if we'll use that for this particular solution. So the idea now is I'm going to construct this point A prime along segment PC, so that A prime P, so that A prime P is congruent to AP. And what does this do? Well, the thing that this does in particular, right, is that because this is a isosceles triangle, right, you get that these two angles are equal, right, and the sum of the angles of a triangle is 180 degrees. So it will follow that, yes, these two angles will have to be equal to each other, and they'll have to be equal to 60 degrees, and so you get that this is an equilateral triangle, right, and so you get that all angles of A prime AP are equilateral, and you get that all sides are equal, right? So that's just, so this point A prime, when we construct this point A prime, will actually make it so that A prime AP is equilateral, okay? And so now, right, this is exactly what I meant by one-dimensionalizing the problem, because now the idea is you have AP, A prime P is equal to AP, right? And so if you can show that A prime C is equal to PB, right, then you'll get that AP plus PB is equal to PA prime plus A prime C, which is, and you know that PA prime plus A prime C is just equal to PC, right? And so we will have successfully proven that AP plus BP is equal to CP now, if we can just show that A prime C is equal to PB. And so how are we going to do that? Well, to do that, we'll actually be using a pair of congruent triangles in this diagram. And so can you see which two triangles we'll be trying to prove are congruent to prove that this result is true? Well, I'll actually tell you which triangles we're trying to prove are congruent. We're going to try to prove that triangle A prime AC is congruent to triangle APC. And there's actually a couple ways to do this. The first thing that you can notice, is that if you look at angle A prime, if you look at angle ACB, it's equal to 60. So actually, let me just do this really quick. You know that angle ACB, sorry, this is going to be a little bit messy. You know that angle ACB is equal to 60 degrees because triangle ABC was equilateral, and because triangle PA prime is equilateral, you get that angle PA prime is also equal to 60 degrees, right? And so if you subtract this common angle, A prime AB, from angles CAB and A prime AP, which we know are congruent given they're both 60 degrees, if you subtract this common angle from, if you subtract this from both of those angles, CAB and A prime AP, what you'll obtain is that you'll obtain that P prime, you'll obtain that BAP is congruent to A prime AC. Okay, so let me mark that in. Hopefully that was clear to you why that was true. I'm going to just erase these 60-degree angles now because we actually won't be using them, right? So we get that PAB is equal to angle A prime AC, right? And we got that from those common the 60-degree angles, and then we subtracted A prime AP, A prime AB from both of them, okay? And so the next thing that you can notice too, right, is that because AP is an arc, you get that angle ACP is equal to angle ABP. And so you obtain that, right, by the inscribed angle theorem, you obtain that these pair of angles are equal. And now it will follow, by, sorry, get my marker here. It will now follow by side, angle, angle, side, angle, angle, right? I'm not going to just write everything out, right? Because it's just going to take up a bit of space, right? But you could see by side, angle, angle that the triangle PAB is congruent to triangle A prime C in this diagram. And so because of that, you can look at corresponding parts of congruent triangles to see that A prime C will be congruent to PB. Because these two, so these will be corresponding sides in these two congruent triangles, and now we can conclude that these two are congruent. And for reasons that we discussed before, we're now done because we can now say that AP plus PB is equal to A prime P plus A prime C, which is just equal to PC, the length of PC. And so, yes, and so this was actually just the overall strategy. Again, you can see how we dimensionalize the problem by looking at these segments here and one-dimensionalize it by turning it into a one-dimensional problem on line, the sum of lengths into a one-dimensional problem in the sense that we're now looking at this, we're trying to show this is equivalent to this thing that occurs on line PC, right? Because now we have, because once we show that these two things are equal, you get that all these are desired to lengths that we're summing are all on one line, and they happen to be on the line that we're trying to prove is equal to the third segment's length, right? So that was sort of the core idea of this solution, was to look at the problem, try to construct equilateral triangles, and one-dimensionalize the problem. And I said that there's actually another way to prove that these two triangles were congruent here. There actually is a way to prove that these two triangles are congruent here. And you can do that. The other way to do it is to actually notice that AC, right, because triangle ABC is equilateral, you can also notice that, I'm sorry, I'm just going to denote segment congruence with, yeah, I'm just going to do it with this. You can notice that AC is congruent to AB. Sorry, I used a lot of ticks before, and I don't want things to get confusing, right? And so actually it turns out also you can conclude by side angle side, right? So we don't know this yet, right, this purple thing, right? You can also conclude by side angle side that A prime AC is congruent to PAB, right? And that's also another way to conclude that. And then once you have the congruent triangles, you can proceed in the same way. So either of those ways work for proving that those two triangles are congruent. And that was the first solution that I'll present to this problem. So I wanted to show you a slightly different solution to this problem as well, besides a constructive one, which we'll do now. There actually are other constructive proofs, or there actually was another constructive proof that I found to this problem, but unfortunately I do not want the video to be too long, and I actually did want to get this other idea in as well. But if you guys do want to see that other constructive proof, let me know in the comment section below, and maybe I will link a new video with the other constructive proof that I found as well, which still involves creating equilateral triangles, but it's not but it's done in a slightly different way. So it's a different construction. Or if you guys actually find constructive proofs of your own, or just solutions in general to the problem, just feel free to put them in the comments section as well. But for the second solution I wanted to present for this video, there's actually a really sort of short non-constructive proof to this problem if you happen to know a theorem called Ptolemy's theorem. So Ptolemy's theorem states that if you have a cyclic quadrilateral, right? If you have a cyclic quadrilateral, and it turns out that summing up the products of opposite sides, so maybe summing up the product of these two blue sides and the product of these two yellow sides, these are the opposite pairs of sides, is actually equal to the product of the diagonals of the cyclic quadrilateral. And so how can we apply that here? Well, the first thing that I'll say is you can basically assume, like by scaling, if you scale up the diagram or scale down the diagram, it will not change the result of the problem, given that, right, because AP plus BP is equal to CP is a linear result. It doesn't matter if you scale the diagram or not. It's the result will still hold true, right? And so we can assume that the equilateral triangle has side length 1. And when we do this now and we apply this Ptolemy's theorem, right, if we do the product of opposite sides, the first product will be AP times 1, right? The second product will be BP times 1. And this should be equal to the product of the diagonals, which is CP times 1. And when you do this, right, yeah, and so this is actually just exactly the result that pops out. Because, yeah, so this actually that's just a one line. If you use Ptolemy's proof, it actually becomes one line as to why AP plus BP has to equal CP. And so, yeah, I thought this was actually a really nice application of Ptolemy's theorem. I'm not sure if it's a Ptolemy's theorem is something that's covered in a traditional high school geometry course. It definitely is useful for some of the high school math contests that are offered, but it's a useful problem-solving tool, that is. But if you guys did happen to know Ptolemy's theorem, this is actually a pretty trivial way to prove this result without any of the constructions at all, even though I think that the constructions are actually quite beautiful. But In any case, whether you did it, whether you thought of a construction, whether you didn't, or whether you're just here to watch the video just to see the solution in general, I just wanted to thank you guys for watching the video. I hope you enjoyed this problem as much as I did. And yeah, I guess I'll be seeing you guys next time.